All right, so we're going to talk about the average value of a function here, sort of going back and picking up one little thing that we didn't get into when we were doing integrals and such. And so if we've got a nice little function here, we want to find its average value. One thing that if you sort of think about it as like a temperature during the day, so maybe the temperature started at 7 degrees one day and went down to 3 over the course of the day. One thing that meteorologists would do is they'd say, well, the average temperature is simply the average of the high and the low. And so if the high temperature was 7 and the low temperature was 3, then we could say the average temperature is 5. And for this particular day, that sort of looks reasonable to say, yeah, the average temperature was about 5, right? So sort of right in between the 5 and the 7. Even if we come to something like this, where again, maybe this is more like the temperature of the day would normally be. So it sort of starts somewhere, 1, 2, 3, 4, 5. And then it sort of slowly picks up steam and gets up to 7, and then it cools down and gets down to 3, and then it ends up back at 5 again. So the high was 7, the low was 3, and the meteorologist would say, okay, well, we're going to average those and we get 5. And again, I think most people would say, yeah, that's pretty reasonable, right? That's sort of a reasonable estimate of the average for the day. Mathematically, the problem with taking the high and the low and averaging them for a sort of generic graph is you can get into situations like this. And so here we have a maximum of 1, 2, 3, 4, 5, 6, 7, 8. And a minimum of 1. And so if we play that average game again, the average of 8 and 1 would be 4.5. 1, 2, 3, 4, so somewhere up here. And the problem with saying that this was the average temperature for the day, of course, is that it didn't spend very much time at all above 4.5 degrees. It was just this little bit of time it was above 4.5 degrees. Most of the time it was below 4.5 degrees, and in fact it was well below 4.5 degrees. And so even though the meteorologist would maybe still say the average temperature for the day was 4.5 degrees, mathematicians aren't going to. They're going to want some other better way of describing that average, and that average needs to take into account the fact that it didn't spend very much time at the high temperature, and it spent a lot of time at the low temperature. And just to sort of cut to the chase, basically what we do is we think about the area under this whole graph, right? And so notice this is getting a fair amount of area because the temperature was high, but it's not very wide because it wasn't there very long. And then here, it's low and it's continuing for a long time, right? And so we think about that area and we think about, okay, how could we get that same area with a constant temperature for the entire length of the day or whatever we're doing? And so how do I find the area under the curve? I integrate the function, right, over my interval, right? And so that's going to find that shaded area. I would then divide by how long that interval is. So in this case, that would be b minus a, and I divide, right? And so if I take the total area and I divide by the width of the interval, that's going to give me the height of the rectangle that has the same area. And so in this case, it would probably actually be lower down here, lower than 4.5. And so this would be the height that gives me that same total area as the function itself. And so this is yet another thing to add to your memorization list. This is the average value, zoom out a little bit here, average value of f of x on the interval from a to b. Right, so average value of f of x on the interval from a to b. And so again, hopefully it makes sense why. It's easier to memorize if you understand why. So we find the total area, we divide by the length, and that gives me the average height, basically. Average height, the height of the rectangle with the same area. This formula leads to another theorem, which is also on your memorization list. It's called the MVT, which we've seen before. So mean value theorem. And we already have that, so you might be saying, well, we can't have another one. So we add this little bit of name to the name here. It's going to be the mean value theorem for integrals, right? And informally, what the mean value theorem for integrals says is, I guess we'll close the parentheses there. So mean value theorem for integrals says says that a function has to equal, a continuous function I should say, has to equal its average value at least once on the interval, right? And so if f of x is continuous on a closed interval, right, then there exists a c in the open interval, right? So a c somewhere in the open interval, such that the value of the function at c equals that average value that we just talked about how to calculate. All right, so you find that average value of the function, and the function has to equal that at some point. And that most people realize when they think about it graphically, it's sort of common sense, right? If the function's continuous. If the function doesn't hit its average value and it's continuous, then it would either need to all be above the average value or all below the average value. And of course, if it was all above the average value would have to be higher. If it was all below the average value would have to actually be lower. It's probably a good exercise to spend a minute thinking about what the original mean value theorem said and how it compares to this. So this is the mean value theorem for integrals. That's it. Thanks.